All right. So 14.6, as you can see, is on, I should say, triple integral. Triple integrals in cylindrical and spherical coordinates. And so, like I said during the, well, I guess it was on the, in that homework exercise, when you're switching to cylindrical, essentially you're just doing an integral and then you get to the double. So you have a triple integral, you basically just peel off one layer and then you switch to polar coordinates. We'll do it all in one step, and that'll be what we call switching to cylindrical. But I wouldn't get too bogged down on it because, like I said before, you know, with that example we had earlier, you had sort of a cylinder on its side, and so it wasn't natural to describe that in cylindrical coordinates the way we have, but it would have been natural if you'd looked at it, you know, from another angle. And so the idea of switching to, you know, or integrating one variable and then switching to polar coordinates can be done. So we'll come back to that in a second. But I wrote over here, right, so let me just, we're going to do spherical, cylindrical, right, so we know, and always nice to remember identity that z equals z, right, treat z the way it was, x squared plus y squared is r squared, x is r cosine, y is r sine of theta, and like we had said before when we were doing polar coordinates, the change in area, the dA was r dr d theta. Since you're leaving the z alone, oh, I put a v here. Right. When you switch to polar coordinates for triple integrals, the dv gets replaced with basically dz and then r dr d theta. We just write it all. So let's try some examples here. So this first one will just be switching to cylindrical. We'll come back to spherical in a bit. So find the triple integral of y dv, where E is bounded below by z equals x plus 2. Bounded above by and below by the xy plane, and is between So again, our first step is to draw this region. And I don't know that I really care about drawing the entire region. You were told it's bounded above by something, right, and below by something. And so I guess I would take that as truth, right? You have the top is going to be this guy, right? Z equals x plus 2, which is a plane, right? So you have a plane coming through space. The bottom is the xy plane, so that's sitting down here. And then you're between these two guys. So let's focus on this. X squared plus y squared equals 1, and x squared plus y squared equals 4. So what do those represent? Circles, but in 3 dimensions, cylinders, right? That go up the x-axis, or the z-axis. So you got a circle of radius 1, right? And then you have a circle of radius 2. And then these are both just getting pulled up like that, right? Okay. That's actually probably enough to do the problem, because you see you have a top of this function, right? And then a bottom of 0. And so you probably don't need to draw any more. In this case, you know, if we did this, our plane right? If you plug in x equals -2, it's terrible, should be there. If you plug in x equals -2, right, you're at this point, your z would be 0, and so this thing looks like a plane that's here. You got the cylinder, and then it's capped off by this plane that kind of slices through it. I don't know that I even want to. I'm trying to draw it now, but I don't really want to. I can't stop myself though. Once we get here, we're going to be up about 4 units. So you're basically going to get something that looks like that. I don't know if that makes any sense to anybody. But you'll basically have, right, cylinder, cylinder, and then sliced through by this plane. And again, all we really care about is making sure we can figure out what the top is, what the bottom is, and then collapse down. And so the collapsing down in this case is really easy. So this triple integral, okay, we're going to convert over to cylindrical coordinates. So what's the dv get replaced with? R dv dr d theta. What's the y turn into?
The y to r sine theta.
R sine of theta. Does that make sense so far? And then be careful because you have to convert your functions as well. So where do our z's go from? 0 till they hit the plane, right? So
From 0 to x plus 2.
this should be more of a straight line. But anyways, I don't want to worry about you. So 0 to, I'll write it like this, x plus 2, but that's not in cylindrical coordinates. So how do we convert that to cylindrical?
R cosine.
R cosine of theta plus 2. Does that make sense? And then we're down in that circle, or that xy plane. We range from r's from where to where? 1 to 2, theta 0 to 2 pi, right? All the way around the whole thing, and you just end up with that. Does that make sense? So let's try to finish this up, I guess. So we're going to end up with what? R squared sine of phi, and there's no z in that to start with, and so when you integrate, you just will multiply by z, right? So we end up with r squared sine of theta, and then r cosine of theta plus 2 dr d theta. Again, this isn't too bad from here. You probably can figure it out, but we'll just take our time and work through it. So we end up with r cubed sine of theta cosine of theta plus 2r squared sine of theta dr d theta. So again, we don't have to worry about the thetas till the very last step. Integrate. Maybe I'll just do these separately. You're going to get r to the 4th over 4, right? So what happens when you plug in 2? Right, so you just integrate the r's like that, plug in your 2, and so you end up with 0 to 2 pi, right? You get 16 over 4, so that's 4 minus 1 over 4, so you get 16, or sorry, 4 minus 1 half, right? So what's that, 7 halves? 7 halves sine of theta, cosine of theta, plus you plug in the 2 here and you get 16 thirds minus 2/3. Is that okay? So you're going to end up with 14/3 here. Okay. How do you finish this off then? Well, let's, so. You might be able to guess the answer right here, but this one is what? Oh, okay. 2 sine. Sine of 2 theta? Yeah. So you could do that, I suppose. Okay. Let's actually, we did that on the last time we encountered this. Let's just do it with a substitution this time. Either way, it's fine. Whatever you feel more comfortable with, go ahead and do. But one way would be just to let u be sine of theta, right? And then what's du? Cosine of theta, theta. And so this becomes 7/2 u du, right? Just this first part. And what would your bound switch to? Sine of 0 is?
Just 0.
0. Sine of 2 pi is?
0.
Also 0. Plus 14/3. And this one, let's just go ahead and integrate. The integral of sine is? Negative cosine. 0 and 2 pi. So integral from 0 to 0 is going to be what?
0.
0. You could do it at 7/4 pi, or u squared if you wanted, but it's 0. And then what's this one? Yeah. Right, you plug in 2 pi, that's the same as 0, so you get 0 as well. Okay. As we've said a couple times, that's not necessarily a wrong answer, but you should always think about whether that answer makes sense. So when we look back at this function, right, we're integrating y, and then look at the region we're integrating over. Does it make sense that you end up with 0? Yes or no? I guess this is the right answer. So why does it make sense? That's what I'm asking.
You didn't have.
So we're integrating the function y, right? And then look at this region, right? It's symmetric across y. So wherever you have positive y's over here, you have the corresponding negative y's over there matching up with it, right? So whatever you integrated that gave you a positive y on the left, you're essentially doing the same thing on the, or sorry, on the right. You're essentially doing the same thing on the left with negative y's. Does that make sense? So whatever positive y happened over here, you're cleaning it out with the negative y on the other side. And so you might have even been able to, you know, if you noticed that before doing the problem, you could have said, that integral is 0, because I see that function is symmetric across my region. I'd be careful about doing that. It's not typically what I want to do.
I want to ask the below side there xy plane, that is not under.
What's that?
Why is not?
So the region is bounded below, so the bottom of the region. This is saying the bottom of the region is the xy plane. Bounded below, so the region sits on top of the xy plane. And then the bounded above, so on top of it is this other plane. Right, think about, you know, above z equals 0, right? Z equals 0 is your plane. You want the region that's above that, so you're only taking the positive part. Does that make sense or not?
No. No, this one makes sense. Above 0 equals to 0 is up, but why that one is going down above by z?
Oh, above, I didn't mean by. Above z equals this. Oh no, that's right. Bounded above by and bounded below by.
But z equals to x plus 2 is above this going this.
So let's look at this. So here's z, here's x, okay? So that's the plane coming out at you. X plus 2 looks like this. Okay, so we have that plane, but it's a whole plane coming out, right? And we're integrating from below this curve and above this curve. They're whole planes, but they're easier to see this way, right? Because then our region is going from x and y go from -2 to -2, right? So we're really only going to integrate the parts that are like between here. Right? You have, so our region looks like this. You got this plane that comes up, right? And then you have this cylinder sitting up there like that, where this, I don't know if I can draw it any better than that. So, I'm gonna draw like this. Here's y now. Right, and then you have, oh, I gotta be careful because I drew my y backwards. This is actually negative y out here. Positive y goes back there, but that doesn't matter too much. The point is, you got this plane slicing through some cylinders, and you're below the plane, this plane, the y equals x plus 2.
So it should be below by z equals to x plus 2 and above by the xy plane, isn't it? Instead of,
No, bounded above. So I think you're getting, bounded means, you're bounded above means this is the cap, this is your maximum. This is the maximum you can get to.
gotcha,
Bounded below means 0 is the minimum you get to.
Okay.
Does that make sense?
gotcha,
Okay.
yep, sorry.
Oh, that's fine. That's definitely a language issue with bounded and what that means for us. So. Yeah, I mean, I guess you could easily have said, right, if I left the bounded out, you could say the region that's above xy, the xy plane and below that. So. Oh, that's fine. I should have thought about that before I worded it that way. Let's see. Okay. Can I erase this then?
Yep.
Okay. All right. So this time I'm just giving you a triple integral, and so I suppose you could try to just integrate this. That's not what I want. I want to, let me maybe say, evaluate by changing to polar coordinates. Not polar, to cylindrical. Now, this is a prime example where I think, right, how do you integrate z? You just square it, z squared over 2, right? And then you could plug in your bounds. That's not so bad. I would probably just integrate it that way. And then once I get to the next integral, I'd look at that and say, all right, that one sort of has a natural, it's natural to switch to polar coordinates then. And so you could do it that way. I want us to just do it all in one chunk. And so what I want us to first do is to draw the region that we're integrating over there. So what region is being described here? And I'll give you some. Y goes from -1 to 1. What's 0 equals the square root of y squared? Remember, those are x bounds, right?
Yep.
So x goes from 0. That's the YZ plane, right? And then until it hits that circle of radius 1. So you're going to get, once you collapse down, you'll be in that circle. And then, and maybe I should draw that dotted. That's not our region, that's where our bounds are, right? So whatever our region is up above this or below this, when we do their intersection, it collapses back to here. So what is that region look like? So let's just draw it here. So remember, these are z values, right?
Yeah.
Z. So in the x, or in the zy plane, what's z equals y squared? You get this parabola, right? And then what z equals the square root of x squared plus y squared? That's just a straight, I mean, if x is 0, it's going to behave like y, right? So you should just get a straight line there. Does that make sense? And then you have the same thing over here. That, and then we're going to take this. I guess that's all I want. And then this gets just sort of spun around like this, right? So you have this bowl opening up on the outside, and then you have a cone cutting through the middle of it. So you got a bowl with that cone cutting through it, and then you're just rotating that around. Does that make sense? So let's go ahead and switch to polar coordinates. You almost don't even need to do that. Or sorry, cylindrical coordinates. You almost don't need to do that here. Cylindrical coordinate z is just z, right? So that sits there just fine. What is the dx, or the dz, dx, dy, what's that become?
R, D, Z, D, R, D, Z.
Okay, good. That makes sense? All right, now we shift our bounds. And so if these are in cylindrical coordinates now, right, it's z equals x squared, so what's that?
R squared.
R squared
To R.
to r. Does that make sense? And then again, now this is where this comes into play. So in terms of cylindrical coordinates, we're just trying to describe that semicircle on the bottom. Let me draw that semicircle again. Where is it? Y goes from -1 to 1, right? And the x is positive. So you might want to always redraw it so that you get the right values. So what's our range here? R goes from
0 to 1.
0 to 1, and theta?
Negative pi over 2 to pi over 2.
Negative pi over 2 pi over 2. Does that make sense? We're getting a little bit tight on time, so I think I'm just going to leave that to integrate. That should be a pretty easy integral, right? You're just going to have polynomials. So. And that's really the point, is that you can, convert over to polar coordinates, get rid of those square roots, and things become a lot nicer. I mean, to cylindrical coordinates, and things become a lot nicer to deal with. All right, let's talk about spherical then for a minute. And then we'll do some more examples next time, but I'm going to be super lazy this time. Okay. So when we convert to spherical coordinates, the dv just becomes rho squared sine of phi d rho d phi d theta. And that order isn't necessarily, you can do it in whatever order you want, but it'll be this. And when we talked about polar coordinates, we explained why it made sense that you needed that extra r in there. And so you just need to do some, geometry and look at the sort of change in volume of a wedge of a sphere. And so this sort of naturally pops out, but I don't want to spend too much time doing that. In fact, I don't want to spend any time. So let me just move on and try it. Let's try an example. Okay? We'll start with one that's just straightforward. 16z dv, okay, over r, where r is the upper half of x squared plus y squared plus z squared equals 4. So this time you probably don't even need the graph, but let's do this. So what's the upper half? Just means, or what is x squared plus y squared plus z squared equals 4? It's a sphere of radius 2. Again, I'm not worried about my drawing here. And we just want the upper half, right? So we're just talking about that piece there. Does that make sense? So you got that top half of the sphere. And so when we want to integrate that, we convert to polar coordinates. Let me just do this off to the side. So dv becomes what? Rho squared sine of phi d rho d phi d theta. What does z become? So
Rho
we're-
square times, no square. Rho times.
Rho times cosine of phi. Again, you're just following that formula that we had before, right? That's your z right there. This whole bit here, that's your dv, right? You're just replacing those things. And then that region is nice and easy to describe in terms of polar coordinates. Where do our rows go from? So our distances all are going to go from 0 till you hit the sphere, so 0 to 2. What about our phi?
0 to 2 pi?
No?
Pi over 2.
Yeah, it depends on what, be careful. The phi is the vertical one, right? From the positive x-axis, or y-axis. So you're from 0 to pi over 2. And then for all of those, we let the theta run all the way around, right? So 0 to 2 pi. Is that okay? All right. So it's a lot to chew on, but hopefully that's not too bad. Let's write this out. 0, 2 pi, 0 pi over 2. 0 to 2, and we end up with rho cubed, cosine phi, sine of phi, d rho, d phi, d theta. Okay, so when you integrate with respect to rho, you get
2 rho fourths.
rho to the 4th over 4, right?
You're missing a 16 from the
Yeah.
Oh, did I?
exam, the beginning.
Oh, I forgot there was a 16. Thank you. All right, that 16's been there all along. So what did you get then? You should
4
get
rho
4 rho to the 4th.
cosine
0 to 2, right? And so plug that in, 64. Oops, 64 cosine phi sine phi. Oh, I dropped my 0 to pi over 2. D phi d theta. This time let's do it the other way. So 0 to 2 pi, 0 to pi over 2.
32
I can replace the cosine of
sine
sine with sine of 2 theta, right? And I had, but I needed 2 of those, right?
theta or c?
What's that? Oh, phi. Okay, and then d phi. All right, and we're almost done with that. So, what's that give us? Then 0 to 2 pi, integrate.
Negative 16 cosine 2.
So let me just do it this way. 32 and then negative cosine of 2 theta over 2, right? And then 0 and pi over 2. And then d theta. So that'll give us, well, you said it, right? It'll give you 16. And then you plug in pi over 2, so you get cosine of pi, right?
32?
Well, yeah.
Is there?
You'll get 16 minus a negative 16, right, when you plug in the 0. So it should be 32 d theta. And then that'll be just 32 times theta, so you'll end up with 64. Does that make sense? Okay. So again, hopefully you see that this, the idea of transitioning over becomes nice and easy for certain types of integrals. Okay, so I guess my directions here are to evaluate this by switching to spherical coordinates. Okay. So you first want to determine what region is being represented here, and then make your switch over. And so I think what I'll do is we'll draw the region down below here, okay, and then over here we'll make our switch. And so before we even worry about the region and changing the bounds, what is the function going to be replaced with? X squared plus y squared plus z squared?
With b squared.
Yeah, the rho squared. And then the dz, dx, dy.
0 or 0.
What is it? I guess I erased
Rho
it.
squared.
Rho squared.
Sines,
Yeah, rho squared, sine of phi,
and
then-
rows, d.
then d, your three variables, right? That make sense? So again, this part right here, oops, this part right here is all just replacing the dv, right, which is the dz dy, or dx dy, and then this is just your x squared plus y squared. Plus z squared there. All right, so what's this tell us? The y's range from 0 to 3. For each of those y's, the x's are going to range from 0 to, well, to the circle, right? X equals square root of 9 minus y squared is a circle. So you get this, well, I guess I still need to do that dotted thing out here. So that's the region we're sitting up above. And then for everything in that region, our z's go from that square root of y squared, which was what? Oh, the cone, right? That was that cone, a 45-degree cone. So you have basically this cone sitting down at the bottom, right? And then what about on the top? The square root of 18 minus x squared minus y squared is a sphere of radius. So you have this, it's just a quarter of it, right? You're sticking down in just this little piece of it, but you got a cone with that sphere sitting on top of it, a piece of the sphere sitting on it. Okay, so when we switch over, what are our, let's do the phis first. Where does phi go from?
0 to pi over
0 to pi over 4. Remember, that was the one we talked about earlier. We'll have different cones later on, but this is by far the most important one. And other cones, you can kind of figure out what the theta needs to be without a ton of trouble, but we'll see this one most often. Where's the theta range from?
0 to pi.
0 to pi over 2. And again, we're inside that cone, right? And so we go from 0 until we hit the sphere, and the radius of that sphere is the square root of 18, right? So you end up with that. And I think maybe I won't even bother integrating that one. That's pretty easy, right? You'll get rho to the 4th, so rho to the 5th over 5. Plug in your square root of 18. It'll be ugly because you'll have a square root to the 5th power, but it's just a number. And then you just have to integrate the sign, and you're pretty much on your way. So that's pretty easy for that, I think. Does that make sense? Okay. So let's, these examples take a while. Let's stop here. Next time we'll do maybe at least one more of each, of converting to cylindrical and converting to spherical. But go practice, try the homework. We've covered everything that you need to know from there, so you should be able to start the homework if you have